So this is homework 4, part C, where we are going to find the reaction rate of, instead of how on part B we did of just chemicals, now we're going to do a reaction rate. So let's first draw out the catalyst boundary, what this looks like. So the catalyst, this is the catalyst surface area. And the chemicals go up to the bulk area. So ethanol goes down, acetaldehyde goes up towards it, and hydrogen goes up towards it also. And like I said, this is the bulk. And the mole fraction of ethanol, so it's Y1 is equal to 0.6. The mole fraction of acetaldehyde is 0.2. And the mole fraction of hydrogen is also 0.2. And the other knowns that we have, we know that pressure is equal to 101.3 kilopascals. Temperature is 548 Kelvin. And we also know that this reaction is a first order reaction, so that is 110 moles per meter squared second mole fraction. Perfect. And then we also know the diffusion coefficient. So from the fusion coefficient from ethanol to acetaldehyde is, what was that? 72 millimeters squared per second. From ethanol, sorry, I'm getting a little sick. From ethanol to hydrogen it was 230 millimeters squared per second. And from acetaldehyde to hydrogen is also 230 millimeters squared per second. So then we're just going to convert these to meter squared per second, so it's easier SI units to deal with, so it'd be meters squared per second to the sixth. All right, and then now we also know that the distance that the diffuses through is 1 millimeter. So yeah, this distance, 1 millimeter, which is also equal to 1e negative 3.63 meters. All right. Now we're gonna move over to the Stefan-Maxwell equations. Oh, Maxwell. So that general equation is the driving force of I is equal to the gradient of the mole fraction of I over position, which is then equal to the summation of the mole fraction of I times the molar flux of J minus the mole fraction of J times the mole flux of I times over the concentration times the diffusion coefficient from I to J. All right. And like in part B, we explained that we have to do the steps. Oh, it's starting to rain. So like the scale position. So we know the scale position N is equal to position Z over the length of the reaction. So then we can take the derivative of the position equal to the derivative, or the derivative of the scale is equal to the derivative of the position over the distance. So then this is also equal to the derivative of the position equal to the derivative of the scaled times the length. So then we can take that, and that would be equal to the derivative of the mole fraction I over the derivative of position is equal to the derivative of the mole fraction of I over the scaled position times derivative of the position over the scale position. Oh, this is over. Let's see. All right. So now we're going to write the Maxwell-Stefan equations for ethanol and acetaldehyde. We don't have to do it for hydrogen because that'll just be redundant, because y1 plus y2 plus y3 is equal to 1, so just like cancel out if we wrote the third one. So first we'll write it for ethanol. So that would be driving force of 1 of ethanol is equal to the derivative of the mole fraction of 1 over position is equal so this is equal to y1 mole fraction of 1 times the molar flux of 2 minus the mole fraction of, not 2, it'd be acetaldehyde, mole fraction of acetaldehyde times the molar flux of ethanol times the concentration times the diffusion coefficient from 1 acetone or ethanol to acetaldehyde. And now we'll write the scaled equation is the gradient of the mole fraction of 1 over the scaled position is equal to the length times I forgot to write the second half, plus, because we did ethanol to acetaldehyde. Now we have to do ethanol to hydrogen. So that is mole fraction of ethanol times the molar flux of hydrogen minus the molar flux of hydrogen the mole fraction of hydrogen times the molar flux of ethanol times the concentration times the diffusion coefficient from 1 to 3. All right, so now the scaled Maxwell-Stefan equation is this. All right, and for acetaldehyde, it's the same thing. So yeah, it's the same equation, just it's the driving force of acetaldehyde. Just everything in this first term is flipped. But the diffusion coefficient stays the same. And the second one, it's the mole fraction and the molar flux of 2. And then the diffusion coefficient changes from 2 acetaldehyde to hydrogen. And then same for the scaled. So the scaled it's mole fraction of acetaldehyde over the scaled position is equal to the length times all of this. Now, for our guess when we go to take this to Excel, we know that okay, so we know that this is approximately equal to 1. So is this. So is this. And so is this. So we are going to take the this to make the guess. Yeah, but this should be okay. I just forgot to change this first term. Yeah. Okay, so we know that concentration is equal to pressure over RT. So the molar flux of 1 is equal to I'm also taking this. So we know that it's equal to the concentration times the diffusion coefficient from 1 to 2 over position, which is then equal to pressure times the diffusion coefficient from 1 to 2 RT times the length. And now for the estimated guess, since this is a first order reaction, we have to relate that into this guess to let you know how much methanol is in a certain area. So it's Y mole fraction of 1 times the molar flux of 1 is equal to the reaction rate. So then for our guess, Y1 would be equal to the absolute value of the reaction rate over the molar flux. It's actually the opposite. It's the molar flux over the reaction rate. And then 1 is equal to Y1 and then Y2, we're just guessing it to be 0.5, half of it, and then Y3 is equal to 1 minus Y1 minus Y2. So now we're going to go to Excel to solve. So this is homework for part C, part 2, where we are going to be using Excel and using the Maxwell-Stefan equations to figure out the boundary conditions and the reaction rate per catalyst. So let's first, I'm going to be looking over here because it has my iPad and what's on the screen, it's on the screen, it's too small for me to read. So let's first input the data that we know. So we're going to do y1, b, y2, b, which stands for ethanol at the mole fraction of ethanol at the bulk, mole fraction of acetaldehyde at the bulk, and then y3 mole fraction of hydrogen at the bulk. So at the bulk, we say that it is 0.6, 0.2, and 0.2. And then we have the mole fraction at the catalyst surface of ethanol, acetaldehyde, and hydrogen. Alright, and then our guess for this, I have to put in my other stuff first. Yes, okay. So we know that D12 is equal to 72 to the negative 6. Diffusion coefficient from ethanol to hydrogen is 230 to the negative 6th, and the diffusion coefficient from acetaldehyde to hydrogen is the same thing. All right, and then we know pressure, temperature, R, and C, and the pressure is 101.3, and that is yep, and then temperature is 548 Kelvin, and then R is 8.314, and then we know that concentration is equal to pressure divided by pressure divided by temperature and multiplied by the gas constant. All right, and then we also know our length, which is 0.001, and then the derivative of that, we're going to do that equal to divided that by 1,000, because we're going to do 1,000 steps. All right, and then we know the rate constant, or the rate constant is just 10. All right, and then we also know that N, what is it? It's the net flow, or the net flow, or the molar flux. The molar flux of 2 is equal, or of acetaldehyde is equal to the molar flux of hydrogen, which is also equal to the negative molar flux of ethanol. All right, and then so then that leaves N1 so our guess for N, the molar flux of ethanol was, we're going to do equals a negative pressure times, let's just turn these into formulas now. Okay. Let's just do, instead of a period, we'll do a comma. All right. So yes, so from selection, okay. Okay, so now we'll do this as equal to negative pressure times diffusion coefficient 1 to 2 . Why is that not working? Why is that not working? All right, That was weird. Okay, divided by R times temperature times our length. All right. Let's change the okay. Oh. All right, and then this is equal to absolute value. One. All right. So then now we can calculate y1s. So that is the absolute value of N1 divided by our rate constant. Okay. And then this is equal, we guess 0.5. And then this is equal to 1 minus y1 minus y1 minus y2. All right, perfect. So this is e to the fifth. Okay. 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 So now we are going to go into solving our equations. So this is our counter. This is dz. This is y1, y2, y3, dy1 dz, dy2 dz. Alright, so this starts at 0 and then solves. Wait, no. This is dn. Alright. And then insert. No. Format. Wait. Oh, no, fill. There we go, series. There we go. Okay, so to 1,000. And then columns. There we go. Okay. And then now dz is equal to this, this times dz. Alright, and now drag that down. And it should be Yep. Okay, so now this one is equal to this. This is equal to this. Why? What is happening? Goodness, what is happening? Okay, this is equal to y2s at the surface, or the mole fraction of acetaldehyde at the catalytic surface, and then this one is equal to the hydrogen, mole fraction of hydrogen at the catalytic surface. Okay, so now we're gonna fill in these equations. So for ethanol, we know that it is the distance times y1 times mole fraction of 1 minus mole fraction of 2 times the flow so it's times the flux of acetaldehyde minus mole fraction of acetaldehyde times the mole flux of that is ethanol, and then this is all divided by concentration times the diffusive coefficient for ethanol to acetaldehyde. All right, then this is added to the mole fraction of ethanol times the molar flux of hydrogen minus the so I did the mole fraction of oh wait, no. So I'm first looking at this one. I'm getting confused because all the equations are next to each other. Okay, so it's, I'm should just delete this so I don't confuse myself. So yeah, I already did that one. All right, so yeah, now it's the mole fraction of ethanol times the molar flux. What is happening? Times the mole fraction or the molar flux of hydrogen minus the, oh my goodness. Okay. Minus the mole fraction of hydrogen times the molar flux of ethanol. And that's all divided by the concentration times the molar diffusive flux of 1 to 3. Yes. Okay. Oh no. So now this is the same. Oh goodness. It's basically the same, but then you just move it to, instead of y2 or y1, it's y2, so it's G and 1, and then it's F and 2, or the diffusive concentration times the diffusive flux of 2. All right, and then it's mole fraction of 2 times the molar, or the diffusion flux, or the molar flux of hydrogen minus should be G, or yeah, that's H, and that's and 2 instead, and then it's diffusive flux over of 2 to 3. Okay. So yeah, it's so now we use Euler's law. So it's where you were plus where you are times that. Alright, and it's the same for where you were plus the distance times the step. Alright, and then this is equal to 1 minus, alright, and then you bring this one down, alright, perfect. Let's see, so now down here it's the bulk, and so for y1 it's pretty off, y2, and yeah, these are way off where we wanted them to be So let's bring them up here. So y2b or y1, I'll do y1, y2, y3. y2, y3b, and that's equal, what was that? That's f1002. Yeah. G1002. Oh. G1002 equal to H1002. Alright, and then we wanted this, the mole fraction of ethanol to be 0.6. We wanted the mole fraction of acetaldehyde to be 0.2, and the same for hydrogen. So now we're gonna subtract these and then square it. And now the sum. Alright, and now we want to minimize that. So we're going to use solver. Minimize by changing I think it's these. Yeah. I'm going to minimize this by changing these. Alright. Now solve. Okay. So let's see if that brought it closer to the values that we wanted. Not exactly. There must be something wrong with one of my equations. Alright, I figured out what I was doing wrong. I had some of these equations wrong. So then I went into solver and I minimized it, changing the molar fraction of the surface of ethanol and acetaldehyde, and that brought it back down to what we wanted each mole fraction to be. And so then that gave us a mole fraction of close to 6 for ethanol, close to 2 for acetaldehyde, and close to 2 for hydrogen. So now in the next part I'll be showing the surface mole fraction of ethanol is 6, and how varying the surface reaction will change the diffusion coefficients. So this is homework. Alright, so now we are going to show how the surface area reaction rate constant to show the extremes that impact the surface and the bulk. So we had our initial guess being this, so we're going to change that to the reaction rate times the surface area. So now you can see how doing that, it makes the bulk and the surface area mole fraction is very, very similar, which means that the reaction rate is happening too fast, or too not happening fast enough, so that it's just happening very, very slowly, so it's like only changing a little bit.